Hello, this is Vincenzo. I'm gonna be making presentation for group project. The topic of our project is quantum key distribution with high loss toward global secure communication, which is by other adapted from WY Hauser phrases Robert Led 91057901 in 2003. In our group project, we have five members in our group. Piper Mishra 21B0671, Tenzin Jamba Mishra 22B1808, Beska Mishra 22B1834, and this is me, Min Kansen 24B0084, and the last but not the least, Yash Gupta 22B1813. For abstract, we propose a decompressed method to overcome the Fordham nervous speeding attack for the Bernard Bastard 1984 quantum key distribution protocol in the presence of high loss. A legitimate user internationally and randomly replace signal passed by multi-photon press decompress, then they check the loss of decompress. If the loss of decompress is abnormally less than zero signal press, the whole project protocol is aborted. Otherwise, to continue the protocol, they estimate the loss of signal multi-photon press based on the decompress. The estimation can be done with an assumption that two losses have similar values. For introduction, quantum information processing. Quantum system enables certain computational and psychographic tests that the infeasible for the classical counterpart. These include quantum cytography, quantum computation, quantum metrology. Beyond their practical significance, their capabilities and also have profound theoretical and physiological implications. The BBA4 quantum key distribution QKD protocol among various quantum information processing protocol. The Bennett Restored 1984 quantum key distribution QKD protocol stand out as one of the most promising. It is anticipated to be the first practical implementation of the quantum information processing. Challenges in QKT implementation. Despite this potential, the practical realization sought QKT for global secure communications face significant challenges. Distance limit. QKT implementation has been successfully demonstrated over a distance of 10 kilometers, extending that the range of remains a critical challenge and noise and decoherence. Like classical signal, quantum signals are sus- susceptible to noise and decoherence, impacting their integral over long distances. Overcoming distance limitation. Quantum repeaters. A natural approach to extending QKD distances is amplifying quantum signal at intermediate location. However, the no cloning theorem prevents straightforward implication amplifications of the quantum signal. 3. Quantum repeaters offer a potential solution allowing quantum signal to be transmitted through noisy environment. Unfortunately, current technology makes quantum repeaters difficult to implement. Alternate approach Alternated approach surface to satellite free space QKD. One of the most promising alternatives is surface to satellite free space BBA4 QKD. However, the method suffers from high photon loss. High loss poses a suffering to the BBA4 protocol, making it vulnerable to photon numbers within PNS attacks. Hence, our purpose is to propose the decompressed methods to overcome the PNS attack for BBA4 protocol in the presence of high loss.
Hello, everybody. My name is Tenzing. So I'm going to introduce to the PNS attack. Assumptions that Alice, as one of the legitimate participants, uses a photon source with the following emission properties: a single photon pulse with a 90% probability, a multi-photon pulse with a 10% probability. Multi-photon pulses are generally inadvertently, and their emission timing is unknown. The channel loss has a factor of L, which is 90%, meaning it has a yield of 10%, which is calculated by Y. Y equals to 1 minus L. Bob, the other legitimate participant, uses practical detectors that are insensitive to the photon numbers. Now to the photon number splitting, which is the PNS attack by Eve. Eve, as the eavesdropper, employs the following attack strategy. She measures the number of photons in each pulse. If the pulse contains a single photon, she blocks it. If the pulse contains multiple photons, she splits them. She retains one photon. The remaining photons are sent to Bob through an ideal lossless channel. Eve is assumed to have unlimited technological and computational power, constrained only by the laws of nature. Bob receives only 10% of the photon pulses, which aligns with the expected yield. Now, as to the security implications, Eve can extract full information about the key by measuring the preserved photons using the publicly announced measurement basis. Under the best case assumption for Eve, all multi-photon photon pulses are exploited by PNS attacks. If the yield for Y is less than the probability of the multiphotons generation, the scheme becomes completely insecure against the PNS attacks. This is because then has no means to detect any interference by Eve. Therefore, the VB84 protocol to remain secure, the yield must be greater than the probability of multiphoton generation. So the requirements for a secure QKD, which stands for the quantum key distribution, when the yield of Y is very low, an almost perfect single photon generator is required. This requirement has driven the development of single photon sources and their use in the QKD implementations. However, perfect single photon sources are not practically achievable. Now, for the two cases of surface to satellite versus surface to surface BB84 protocol, in the case of surface to surface free space BB84, the single photon condition is nearly satisfied. Surface to satellite QKD suffers from higher loss due to the satellite moving rapidly, the increasing distance between the communication parties. The security of a satellite based protocol depends on the physical security of the satellite. It is assumed that Eve cannot secretly observe the inside the satellite. However, justifying the assumption is challenging. Reflection based protocol. A proposed solution is used to communicate with the satellite equipped with mirrors to connect these surface users. A reflection-based QKD protocol has been explored in multi-user QKD contexts. However, this method introduces even higher losses, making a secure implementation difficult with the current technology. Now, to detect the photon number splitting attack, we use the direct detection methods. One approach is to monitor photon number statistics, which might be disturbed by Eve's PNS attacks. In the case of weak coherent samples states, a simple PNS attack alters the photon number statistics, allowing Bob to detect it. However, Eve can employ a more sophisticated PNS attack that preserves these photon number statistics, making detection harder. Thus, additional countermeasures are required. As you can see in this photo, Alice now sends the signals from the WCP source, which is which is intercepted by the Eve, where Eve, when requires when Even when she gets the multiple photons, she separates one single photon to herself and then gives the other to the other photons to Bob. And if the single photons are emitted by Alice, they are all blocked by Eve.
Hello, I'm Bhaskar Vishwas, and today I'll be explaining the decoy pulse method. Uh, I will explain the core idea behind the decoy pulse method, describe the underlying photon number and coherent state representation, and outline how signal and decoy sources are used to detect eavesdropping attempts. Let's dive right in. The main idea behind the decoy pulse method. At it at its core, the decoy pulse method is built upon simple observation about eavesdropping in a photon number splitting PNS attack. An eavesdropper, typically we will call Eve, can selectively forward multi-photon pulses to Bob while blocking single photon pulses. This selective transmission causes the yield or detection rate of multiple photon pulses to become abnormally high than that of single photon pulses. To counteract this, Alice intentionally and randomly replaces some of the signal pulses which are normally used to encode key bits with specially prepared multi-photon decoy pulses. Since Eve cannot tell the difference between multiple photon pulses coming from the signal source and one from the decoy source, the yields of multi-photon events from both sources should be similar under normal conditions. By monitoring and comparing these yields, Alice and Bob can detect if a PNS attack is underway. If the decoy pulses show an unexpectedly high yield, they know that something is amiss and can take appropriate actions. The photon number representation. Let's now discuss the photon number representation. Consider a quantum source that emits a pulse represented by the ket n containing n photons with probability Pn, where n can be 0, 1, 2, and so on. The probabilities must satisfy a normalization condition, that is this equation, summation of Pn equals 1. Each of these pulses carry one bit of the key. In practical terms, while we ideally want a source that emits one photon at a time, real sources often have non-zero probability of emitting more than one photon. This inherent imperfection is what opens the door to attacks like TNS attack, making it essential to design countermeasures such as the decoy pulse method. The coherent state representation. Moving on, many QKD systems use sources that generate coherent states. A coherent state is represented by mu e to the power I theta, where mu is the amplitude and theta is the phase of the pulse. In order to simplify the analysis and ensure security, we randomize the phase theta. After this randomization, the state becomes the mixed state described by this equation, where rho equals integral of d theta by 2 pi uh, with outer multiplication of this coherent state. This mixed state is equivalently to a statistical mixture of Fock state expressed as this summation p n mu with outer multiplication of n state, with n going from 0 to infinity. Here the probability Pn of mu of emitting an n photon state follows a Poissonian distribution where Pn mu equals e to the power minus mu and mu to the power n divided by n factorial. In other words, once the phase is randomized, a coherent source essentially acts as if it were emitting photon number state n with probabilities given by the Poissonian formula. This is crucial for understanding how the decoy pulse method leverages the differences between signal and decoy pulses. So, what is the purpose of signal and decoy sources? Alice employs two types of sources here, the signal source and the decoy source. What are their benefits? The signal source is used to primarily distribute the cryptographic key. For the signal source, we typically set the average photon number mu to be less than 1. This setting ensures that the source mostly emits single photon pulses, which are ideal for secure key distribution. Decoy source. This source used to detect the presence of PNS attack. For a decoy source, we choose the average photon number mu dash that is equal to or greater than 1, meaning it mostly emits multi-photon pulses. It is important to note that while the decoy pulses have a higher multi-photon component, their polarization is randomized. This randomization ensures that aside from the photon number distribution, the decoy pulses are indistinguishable from the signal pulses. Therefore, if Eve tries to carry out her attack, she won't be able to tell which pulse are decoy and which are the genuine signal pulses. So some detection assumption and yield definitions are given. Now let's discuss the detection part of the protocol. Bob uses practical photon detectors that in general are insensitive to the exact number of photons arriving in a pulse. We define the following yields: Yn, the relative frequency with which an n photon pulse from the signal source is detected by Bob. The corresponding detection frequency for an n photon pulse from the decoy source is named as Yn dash, where both y and yn dash takes value between 0 and 1. An important observation here is that even if some photons in the pulse are lost, Bob's detector may still register the pulse, so the yield can be unique. This is because the detectors are designed only to note the arrival of pulse rather than the count of exact number of photons. The yield formula. Let's now look at the mathematical expression of the yields. For the signal source, the overall yield is Ys, and the yield for the decoy source is Yd, which is given by these two equations, where mu is replaced by mu dash. Otherwise, they are the same. Where Pn and P and mu dash both follow the Poissonian distribution, respectively. The yields Ys and Yd can be directly detected by Bob. We also define the yield of only multi-photon pulses from the signal source as this YSM. That is the summation of Pn mu Yn, where n is greater than 2 or equal to 2. Although YSM cannot be directly measured, it can be bounded through the other yields. To get a better idea of proportions of multi-photon pulses within the overall signal yield, we define a normalized multi-photon yield Y tilde Sn, where it is the ratio between the summation of P and mu and Yn divided by summation of P and mu. This normalized yield represents the fraction of signal yield coming from multi-photon pulses. The key insight is that under normal circumstances, the yields of multi-photon pulses from both the signal and decoy sources should be nearly equal because you cannot differentiate between them. If there is an abnormal discrepancy, it would be a strong indicator of a PNS attack.
Hi, I'm Yash Gupta, and now that we have a very important relation on the yield of the decoy pulse, we'll move forward to some more mathematical quantities that will be useful for defining the security of this protocol. So, firstly, we go forward with finding a bound on the yield of the multiphoton from the signal source. So, for that, firstly, we need to understand why we need to maximize this thing. So Eve doesn't want to uh, let Bob know or Alice know that it is interfering with the communication. So it wants to maximize the yield of the multiphoton as much as possible without getting detected. We can also say Eve wants to maximize this quantity which is nothing but the ratio of the multiphoton from the signal source divided by that from the decoy source. So if A is maximized, uh, the number of times Eve is playing around with the decoy source is much less than the number of time it is interfering with the signal source. Okay. So to calculate a bound on YMS, we should start with first finding a bound on A. So we started with the assumption that the mean of the signal source is much less than the mean of the decoy source. So look at this quantity, which is uh, the ratio of the probability distribution of signal and decoy for two different indices. So if n is less than m, then this ratio will be much greater than this ratio. Now, why is that? We will look at it now. So if you look at the formula for Pn mu upon Pn mu dash and put substitute the Poisson distribution, you get this expression. Now this expression mu upon mu dash is less than 1, much less than 1. So if the index is greater, the quantity will get reduced even further, thus justifying the above relation. Okay, so now we can use this relation to find a bound on A. So if I substitute the value of A, which is this thing, we get a bound that is much less than the uh, probability of two photons for single pulse upon decoy pulse. Now, why is that? Consider this quantity, which is P2 mu by P2 mu dash minus A, which is nothing but the A transferred to this side. So if I substitute the expressions for P2 mu, P2 mu dash, uh, and also A, we will get this expression. Now look closely, the expression in the bracket, this thing. Now I can easily switch the P2 mu inside, and here also I can put the P2 mu dash inside, and I will get this expression. So now this expression is where we will use the above relation, that for a greater index, it is the ratio is much less. So you can see that here, this expression by a simple cross multiplication here, this expression will be 0 for n equal to 2, and it will be more than 0 for n more than 2. So and also we can also see that the equality will hold when y2 is more than 0 and the rest of the y they are 0. Because then all the positive terms will get cancelled and the term for n equal to 2 is nothing but 0. So this thing, the condition that when y2 is more than 0 and the rest of the y's are 0, Eve can get the maximum ratio of A. So this is uh, the ratio that the maximum ratio a Eve can get without getting detected. Okay, so just to rephrase, the final optimal strategy that Eve should adopt is that it should focus mainly on the two photon sources. Just a minute. Yeah. So it should mainly focus on the two photon sources, and for all the other sources, it should block them. And one reason you can give is because since the decoy source has much higher mean, the higher photon pulses uh, they match with they correspond to the decoy source. So by focusing on the sources with less photon number, you can focus more on the signal source instead of the decoy source. So now that was all about Eve, that what Eve should do to get the best out of the situation. Now let's use this information this worst case information for us to find a bound on the YMS. So using the bound on A, we can get that firstly, let me show the expression for YD. So this was the relation that we derived before on YD, and also we have the relation for YMS. So now if I divide both of these and also use the expression for A, not divide, but if I compare both the relation and also use the equation for A, the bound for A, I can get this equation, which is derived from here. This P2 mu by P2 mu dash, I will get this equation. And I can also simply transform this to a normalized function by divided with the total probability for n equal to 2 to infinity. Okay, so this is the bound we get on the normalized YMS, and there are some things that we should must keep in mind, that the P2 mu dash and also this quantity P2 mu by summation over Pn mu, they are both of order of unity. You can substitute the parameters 0.3 and 1.0. This is definitely closely related to 1, both of the quantities. And then we can realize that the yield of decoy and also the yield of the multiphoton from the signal, they are of the same order of magnitude. Now, why this thing is important is that when Bob is receiving the signals, he can easily say that whatever is the in normal circumstances, whatever is the yield of my decoy pulse, it should be same as the yield rate of the signal pulse. So if Eve tries to interfere with the communication anyhow, and Bob sees a slight difference or a significant difference in both of the quantities, he will be able to understand that there has been something going on in between. Okay, so now we have got a bound on YMS and proved a very important point that the decoy pulse can be used to estimate errors. Now let's come to the main task, which is defining a condition for the security of the protocol. Okay, so one thing that we must convince ourselves is that for the protocol to be secure, the number of calls that are rejected, they should be much greater than the attacked ones. Right. So the number of attack pulse is simply given by the probability of the multiphoton pulse times the yield rate of the multiphoton pulse, which has been normalized. So the condition that we started with initially, which was that the yield rate, the channel loss related yield rate, it should be much greater than the multiphoton probability, can be reduced to this expression, which says the single photon, signal source yield rate must be greater than this quantity. Now this is nothing but the number of attack pulse, which has been the yield rate of the attack pulse, which has been taken a maximum over all the different strategies adopted by Eve. So now if we substitute the expression for a YMS, which is this one, this bound for YMS, we easily get a we get a relation on the yield rate of signal pulse and the yield rate of decoy pulse. So now this expression is very useful in defining why the decoy pulse method is much better than a simple BBF4 protocol. Now let's see how that works. Okay, so as we have defined from the very start, both the sources are Poisson distribution. And if we do a linear approximation of the yield rate of decoy pulse and the signal pulse, we will see that it is the yield of the decoy is greater than that of the source by a factor of mu dash by mu. The motivation behind this, if you do a linear approximation, the YS will be proportional to n times mu, and yd will be proportional to n times mu dash. So now if I put this linear approximation in the above relation, I will get this relation. Basically, this is just yd by ys, which has been replaced by mu dash by mu, and it should be less than 1. So this quantity should be less than 1. Now, for a given mu dash, the condition is satisfied only when the mu is sufficiently small, because there's an exponent in the denominator and also a linear term in the numerator, which will be definitely reduced because of the exponent. So whenever your mu is small, your mu dash will be the condition will be satisfied. One example is when you take mu dash to be 1, you fix it at 1, then your mu should be much less, which is about 0.3. Any range between like less than 0.6 works, and then the left hand side of the equation will be satisfied. The left hand will satisfy the relation. For these numbers, the left hand side comes to be about 0.6, which is much less than which is less than 1, and will satisfy our security condition. Okay, so uh, the one thing you can note is that the requirement of this condition is that mu should be anyhow small. So that means your source should be still a ideally not ideal but close to ideal single source. Single source, yeah. But one thing that we can't overlook is that there is no dependence on the channel loss. We started with this condition where y is much more than p multi, and it was very much dependent on the channel loss. But here, after doing the finding a bound on the YMS using the decoy pulse, we can see that the dependence on the channel loss has completely dropped. So it means you can work in any much you can work in an environment with the loss as much as you want, as long as your source has a low mean, your condition will be satisfied. So we started with the satellite to surface protocol where the high loss is very much. So even in that condition, as long as you work on your single source, uh, you can easily communicate without worrying about the surrounding losses. So that was the main result that the paper has proposed. And also we can move forward to uh, applying the same protocol to some more general distributions. We started with considering that both the signal pulse and the decoy pulse have Poissonian distribution, but you can also do the same for different distributions. So consider that the almost perfect single photon detector generator has this distribution where the probability of emitting one photon is 1 minus epsilon, where epsilon is much less than 1, and the probability for the subsequent number of photons is given by this quantity k by L factorial, where k is some constant, and you can see as the I increases, it drops down in an n factorial manner. uh, K has to be a constant such that it satisfies the probability conservation. So the summation of Pi from 2 to infinite should be epsilon, so that when added with P1, we should get 1. So if we do a similar type of calculation we did above for two Poissonian sources, we get an expression which says Ys, the yield of the source, this signal source, should be more than epsilon by this P2 mu dash times yield of the decoy pulse. So we can see that whenever our epsilon is very small, this condition will be easily met. But one issue is that for a small epsilon, when you have such a high yield rate for the signal pulse, your key generation rate should be also much higher. Now, one problem is that the highest signal source rate yield is limited by the technology in the current world. So one important takeaway we can say is that we are in the most benefit when the decoy and the signal pulse are having the similar photon number statistics. We just proved that it works for different also, but it is more efficient when both of them have similar photon statistics. Now we would like to move to a demonstration of the paper using code. Using code. Now I think God one government बता दो start to be depending system. Correct में करना. Sure.
So hello, I'm Vipul Mishra and I'll walk you through the code implementation. Here, we'll explore how normal signal transmission works and what happens under a photon number splitting, that is a PNS attack, and how decoy states help detect such attacks. So now, uh, first go over the simulation parameters, which are mu equal to zero point 0.3. This represents the mean photon number per pulses for signal pulse. Similarly, mu prime, which is for the decoy source, then eta. This is the channel transmission efficiency, meaning only 10% of photons survive the transmission. As we have said, the eta is equal to 1, 8.1. Then we have Nmax, uh, which represents the maximum number of photons per pulses that we consider. These parameters define our quantum channel, which where we will simulate photon yields under normal and attack scenarios. Now, the core of our simulation is based on Poissonian statistics, as mentioned in the above contents as well. Uh, these are used to model the probability of having n photons per pulses. The function uh, that we have developed here, that which is Poisson, with input parameters n and mu. Mu represents the mean, and n is the number of photons per pulses. Using this, we generate probability distributions for both signal, that is P signal, and decoy sources, that is P decoy. These distributions are key to understanding how many photons typically exist in each pulse. Next, we define the function for calculating the yield in both the with the input parameter attack uh, default by default set to false. That is, there isn't any third party involved. So, in the function returns the expected photon yield by summing over all possible photon numbers weighed by their respective probabilities. So, in the normal operation, the YS normal and YD normal, these are the yields for signal and decoy pulses in normal conditions. And the respective yield is calculated using the formula that I have highlighted. So in this formula, uh, the probability for detecting a particular pulse with n photons is eta raised to n, and using that we'll calculate the yield using the formula 1 minus 1 uh, minus eta raised to n. So, and then similarly, we'll also evaluate the signal signal yield in the attack scenario and decoy yield in the attack scenario. Now comes the result part. So here the first plot shows yields in a normal scenario and the second one in the PNS attack scenario. The numerical results highlights the difference between the drop in the signal yield and decoy yield between the both the scenarios. So the drop in the signal yield is around 75%, and the decoy yield is around 38%. So, uh, this simulation reveals a crucial property for the of the decoy states. Normally, both signal and decoy yield should drop by the same factor due to the channel loss. But here, because of the interception of Eve, the decoy yield remains artificially high compared to the signal yield. This discrepancy allows Alice and Bob to detect Eve's presence and abort communication to maintain security. So, this implementation demonstrates the effectiveness of the decoy pulse method uh, in detecting the involvement of the third party and increasing the security of the transmission. This will be the end of our presentation. Thank you for the opportunity.